Thiazoles. I will repeat this once again because there was a power problem. So, thiazoles. These are thiophene derivatives. This is not R, this is I. These are thiophene containing a nitrogen at position 3. So, sulfur in position 1 and nitrogen at position 3. So, thiazole moiety is present in many naturally occurring compounds like thiamine, that is vitamin B1, and the antibiotic, well-known antibiotics, that is penicillins. So we can see here the structures. So this thiazole ring, so sulfur atom in position 1 and nitrogen atom in position 3, it is a part of this thiamine, that is vitamin B1. Similarly, this thiazole ring, it is also a part of the penicillin. There are a number of other pharmacologically important compounds that contains thiazole ring system. So sulfur thiazole, which is used as an antibiotic, and thiabendazole, which is used as an anthelmintic property. So niridol, which is used as the somiad activity. So coming to the synthesis, hand synthesis. There are two different methods commonly used for the synthesis of the thiazole ring system. The first one is the hand synthesis. This reaction involves the reaction of alpha haloketones with the thioamides. We can see here the equations. This is an alpha haloketone and this is attacked by the thioamide. So the sulfur atom is attacking as a nucleophile this carbon atom, displacing this chlorine atom. So sulfur attacks as a nucleophile at this carbon atom and it displaces the chlorine. So it is a nucleophilic substitution. So in another nucleophilic attack, the nitrogen atom will attack the carbonyl carbon and this is followed by dehydration. This H plus and OH minus are removed as water molecule and we get a double bond between C4 and C5 carbon atoms. And here we can see we can vary the substituents in the thiazole ring system at position 2, 4 and 5. So if we have only hydrogens, we get simple thiazole. If we use formamide and a simple alpha haloketone, we will end with thiazole, or we can prepare variously substituted thiazole ring system by having various substituents in the alpha haloketone and also in the thioamide. So we can see here. So in thioamides, R can be hydrogen, CH3, NH2 or SH. So simple thiazole can be prepared by condensing chloroacetaldehyde with thioformamide. You can see here. Chloroacetaldehyde, no substituents at this carbon and this carbon atom, and similarly no substituent at this carbon atom. So simple chloroacetaldehyde, simple alpha haloketone like chloroacetaldehyde reacts with thioamide to form thiazole ring system. Next, Gabriel synthesis. This involves the reaction between stoichiometric amounts of 1,4-diketone with P2S5. So here we can prepare 2 substituted thiazole or 5 substituted thiazole or 2,5-disubstituted thiazole. So we can see here the 1,4-diketone. So here in place of carbon we have nitrogen. It is a 1, 2. So we can start now counting from here 1, 2, 3, 4. It is a 1,4-diketone. It is reacting with stoichiometric amount of P2S5 at around 150 to 170 degree centigrade, where this oxygen atom is displaced by the sulfur. We get sulfur here in place of oxygen. we get sulfur here. Then the resulting compound undergoes. So there is a nucleophilic attack of the sulfur. There is a nucleophilic attack of the sulfur. So there is a shift of the double bond. There is a shift of the double bond here. From this position, it is shifted to this position, and hydrogen comes here. So it is like a tautomerator. This hydrogen comes to sulfur, and the double bond shifts from this position to this position. So now this thiol, it will attack as a nucleophile at the carbonyl carbon. So it is a amide carbonyl group. So sulfur atom will attack as a nucleophile, and this is followed by the removal of OH minus and H plus, resulting in the formation of double bond between carbon and nitrogen, and therefore we get a 2,4,5 tri-substituted thiazole. Various substituted thiazoles can be prepared by this method. The thiazole ring possesses aromatic character, and it is considered as a resonance hybrid of the following resonating structure. It has a considerable aromatic character, and it is prone for electrophilic substitution at position 5 and nucleophilic substitution at position 2. So, thiazole contains thiophene type of sulfur atom and pyridine type of nitrogen atom. So this sulfur atom, it behaves as the same sulfur atom in thiophene, and this nitrogen, it behaves as a pyridine type of nitrogen, that is electron withdrawing in nature. So thiazole is expected to have properties similar to that of pyridine and thiophene, because the sulfur atom behaves as a thiophene sulfur and nitrogen behaves as a pyridine type of nitrogen. Therefore, it resembles in its properties. Thiazole resembles in its property with the thiophene and pyridine. So, electrophilic substitution. So, thiazole undergoes some of the electrophilic substitution. Usually, unsubstituted thiazole may not undergo most of the electrophilic substitution reactions. However, appropriately substituted thiazole can undergo electrophilic substitution reactions, and usually electrophilic substitution occurs at the position 5. So this is not thiophene, this is thiazole. It is thiazole. It is thiazole. This is not thiophene. It is thiazole. It is prone for electrophilic substitution at position 5. 1, 2, 3, 4, 5. So electrophilic substitution usually occurs at position 5. However, unsubstituted thiazole may not undergo all the electrophilic substitution reactions. Here, if we take unsubstituted thiazole, so nitration. So even under forcing conditions, thiazole does not undergo nitration. So nitration is not observed in simple thiazole even under drastic conditions of nitration. So sulfonation using oleum at 250 degrees centigrade in presence of this mercuric sulfate, and thiazole, it undergoes sulfonation, and this sulfonic group is positioned at the 5th carbon atom. So we get thiazole 5 sulfonic acid. So bromination. So no reaction with bromine or chlorine in an inert solvent. So simple thiazole do not undergo bromination. Similarly, alkylation. So alkylation. So in presence of tertiary methyl alcohol and under acidic conditions, thiazole ring does not undergo any alkylation reactions using some alkyl iodide. We have to use some alkyl iodides for alkylation reaction. So it will not undergo any alkylation reaction. So simple thiazole do not undergo any alkylation reaction. So coming to diazo coupling. So no reaction in the case of simple thiazole. So simple thiazole usually do not undergo many of the electrophilic substitution reactions. So mostly substituted thiazoles will undergo these electrophilic substitution reactions. So coming to nucleophilic substitution reactions. So thiazole ring usually undergo nucleophilic substitutions at position 2 of the thiazole ring system. So for example, so here we can see it is a 4 substituted thiazole. So 4 methyl thiazole can undergo nucleophilic substitution and the nucleophile is introduced at C2 carbon. So when 4-methyl thiazole is treated with sodamide and heated to 150 degrees centigrade, we get 2-amino 4-methyl thiazole. Therefore, nucleophilic substitution occurs at position 2 of the thiazole ring system. Similarly, 2-halo substituted thiazole undergo nucleophilic displacement reactions or nucleophilic substitution reactions. Here we can see 2-bromothiazole when treated with ethoxide ion, it forms 2-methoxythiazole by displacing this bromine atom. So bromine is a leaving group here. Bromine is a leaving group. It is displaced by the base methoxyl group. Similarly, a primary amine can act as a nucleophile and it can displace this bromine atom. So to form once again a 2 substituted thiazole. So reaction with aldehydes. The substituted thiazole can react with the benzaldehyde in presence of an acid catalyst. So here we can see 2,5-dimethyl thiazole is reacting with benzaldehyde in presence of zinc chloride and acid catalyst in a condensation reaction. So that means this oxygen and the 2 hydrogens are removed as water molecules. It is a condensation reaction. Similarly, 2-amino thiazole can react with benzaldehyde to give the corresponding azomethyl derivative. So this 2 hydrogens and this oxygen are removed as water molecules. So this is another example of this reaction. 2-amino thiazole can undergo reaction with alpha beta unsaturated carbonyl compound. So oxidation. Thiazole is resistant to oxidation, but 2,4-dimethyl thiazole, that is 2,4-disubstituted thiazole, can be oxidized with H2O2 or peracids to the corresponding N oxide, just like other azoles. Thiazole can also undergo oxidation when it is appropriately substituted in the ring system to form the N oxide. So metallation. On treatment with N-butyl lithium or Grignard reagent, thiazole give the corresponding 2 substituted product. So we get 2-litho-thiazole. When thiazole is treated with N-butyl lithium in ether at -50 to 60 degrees centigrade, we get 2-litho-thiazole. So -50 to -60 degrees. So thiazole react with ethyl magnesium bromide in ether at 0 to 20 degrees centigrade to give a 2 substituted thiazole. So these are some important reactions of thiazole, and earlier at the beginning we have seen its importance. It is thiazole ring is part of many naturally occurring compounds like the vitamin B, vitamin B1, that is thiamine, and it is also a part of the penicillin structure. You can see here, thiazole ring is a part of the vitamin B1, and it is also a part of the antibiotic penicillin. And there are also other compounds of pharmaceutical importance like sulfathiazole, thiabendazole, and neridol. These are some important compounds containing this thiazole ring system.